This is VLSI data conversion circuits, lecture 9. So far we have seen how to make a sampling circuit with hopefully good linearity, in the sense that we learned how to make the resistance of the sampling switch independent of the input signal. Of course, we know how to choose the sampling capacitor, because we know that the mean square noise that sampled onto the capacitor is kT by C. So, given the resolution of our entire A to D conversion system, we can go and figure out how much thermal noise we can tolerate, which fixes the size of the sampling capacitor, and then depending on the tracking bandwidth that we need, we go and choose the resistance of the switch that we can tolerate. Often you do not want to operate on the hairy edge of your tracking bandwidth. So, you want to make sure that the resistance of the switch is small enough that the RC time constant is exceeds that required simply from tracking considerations by a reasonable safety margin. Okay. And let us remind ourselves again, why did we go through, under what circumstance do we need this switch to be linearized by having a constant VGS? Why did we need the switch to have a constant resistance as a function of input? Pardon? Of course, okay. So, in other words, if the input was a continuous time sinusoid, right, and therefore the voltage across the capacitor is also the same sinusoid, assuming that the drop across the switch is very small, then the displacement current flowing through the capacitor is C dV dt, right, and that gets multiplied by the resistance to give you the voltage drop, which is the difference between the input and output just before you turn the switch off, correct. Now, if the resistance varies with input signal, then the displacement current, which is the derivative of the input signal, gets multiplied by the nonlinear resistance and gives you harmonics. On the other hand, once you sample the continuous time input, it is just sampled and held. So, within a clock period, the input voltage is not changing. Now, you might ask, where do you see those scenarios, right? So, the front end of the A to D converter is the one which typically sees this continuously varying signal. Once the signal has been sampled on a capacitor, nobody knows what kind of input it came from, correct. Once it is sampled, it is just as good as coming from DC, you understand, and we may further want to process this signal in some way. For example, I mean, we will obviously need to quantize this input voltage which has been sampled on the capacitor, right. There are many ways of quantization. One, for example, if we were able to make a very coarse estimate of the input, then we could quantize it in the following way. We have the sampled signal on the capacitor, we subtract the coarse estimate, right, and get the difference between our coarse estimate and the actual input, and now we start working on this error or the difference between the actual input and the coarse estimate. I mean, the motivation for this is that it is not always that one is sampling a continuously varying input signal. As we will see going forward, there are many instances where a sampled and held signal has to be sampled again, right, after suitable processing, maybe subtraction, maybe amplification, maybe anything else, you understand. So, if this input was not continuous time, but was was sampled and held to begin with, correct. So, the situation is not like what we had earlier. Earlier we had a continuous time input. Now, if you already had sampled the input, and you wanted to resample this onto another capacitor, you understand. The question I am now posing is, what kind of switch would we need to sample a signal like this? In other words, would we still need a bootstrapped or a gate boosted switch? I mean, by bootstrap switch, I mean the switch where the gate potential is V in plus VDD, right. I mean, as we have seen going through the last class notes, it is a quite elaborate affair, right. So, to linearize the sampling switch, there was a whole bunch of extra paraphernalia needed in order to make that happen. So, obviously, bootstrapping the gate with the input is quite complicated from a circuit point of view. All right. Now, the question I want to ask you is, let us assume for the time being that we have a signal which has already been sampled and held, and we want to resample it onto another capacitor. The question is, what choices do we have for this sampling switch? Is it necessary that I use a bootstrap switch? I mean, clearly a bootstrap switch will work, because I mean, this is just any other input as far as the bootstrap switch is concerned. The question is such a switch with all its extra baggage really necessary, or it is not necessary? It is not necessary in this case, and why might that be?
No, as long as the switch can pass through each of these levels properly, and if the RC time constant is fast enough when compared to these each of those sampled sampling intervals, then it's okay.
Yeah. So, there is a crucial difference between this signal and the sinusoid, which is continuously varying, right, and that is within a clock period this input is constant, which means that if the resistance of the switch, even if it is nonlinear, is sufficiently small, what happens? At the end of the clock period, this voltage will be the same as this voltage, okay, which means the derivative of the voltage is the same as the derivative of the input voltage, which means that the current flowing through the capacitor is what? What is the current flowing through this capacitor if the voltage is of this form? It is 0, right, because there will be a jump in the current when there is a switch, when the input changes at the end of the clock period, but that current will quickly decay to 0, correct, because the rate of change of this voltage is 0 within a clock period, right. So, if the current towards the end of the clock period, which is what you are interested in sampling, right, is 0, then even if the switch is nonlinear, the voltage drop across that switch is 0, which means that there is, in principle, there is no problem with sampling a distorted version of the input. So, in other words, just before you open the switch, and which switch are we talking about? This switch. So, just before I open that switch, the voltage here will be virtually the same as the voltage at the input. Does this make sense? Okay. Now the question is, what happens when I indeed turn the switch off? Alright. So just before I turn off the switch, the voltage to the left and the voltage to the right of the switch are exactly identical, and why? Because the current through the capacitor is 0, which means that there is no voltage drop across the switch, even though the switch can have a resistance which is non-linearly dependent on the input. Is this clear? Of course, when the input changes at the end of the clock period, there is a big difference between the voltage to the left of the switch and the right of the switch, because the capacitor will not allow the voltage to change instantaneously. So there will be a spike of current that occurs, however that will only occur around transitions of the input and will quickly die down, right, as the cycle continues. Does it make sense? So it is often, you will note that bootstrap switches or gate boosted switches are only employed at the continuous time to discrete time interface. Once you have digitized it, once you have sampled the input with sufficiently good fidelity, after that most of the time simple switches are all that are needed. Is that clear? So what kind of switch do you think is a good candidate here? A transmission gate is in principle good enough, because the signals can go all the way from 0 to VDD, and a transmission gate allows you to sample the input without any problem. Does it make sense? All right. So now let us examine the process that happens, or what happens when you turn the switches off. So why is a MOS transistor conducting in the first place? Let me now make a blow up of the transistor. So let us say this is Vin, this is VDD, and this is the sampling end of the switch. This will also be equal to Vin. All right. I am assuming a held input, so that the current through the MOS transistor is now 0. Is this clear to everybody? The nature of the difference between a continuous time input and a sampled and held input. Okay. Now why is a MOS transistor conducting? There is a channel, when you apply VDD, there is a channel charge. The channel charge is what is responsible for conduction, right? And given VDD and Vin and the dimensions of the transistor and its properties like threshold, etc., what do you think is the amount of charge in this channel? To a very crude approximation, it is WL times Cox times VDD minus Vin minus Vt, right. This is, please note, only a very crude approximation and is not quite correct. A detailed analysis of this charge will reveal that this charge Q is some nonlinear function of the input and a whole bunch of other things. I mean, one straight way of seeing that is that the threshold voltage itself through the body effect is dependent on Vn. So even this crude approximation is telling you that the channel charge of a transistor depends on the input. Does it make sense? So if the channel charge of an NMOS transistor depends on the input, it follows that the channel charge of the PMOS transistor also depends on the input, all right. So when this potential at the gate goes from high to low, And when does it go from high to low? When you are transitioning from the sample phase to the hold phase, that is when you are turning the switch off, and turn the switch off, what are you going to do? You are going to yank the gate towards ground. Now the question is, what happens to this charge? Clearly, when the gate is connected to ground, what is the channel charge? Channel charge is 0. So, when the gate was high, the channel charge was this. When the gate is low, the channel charge is 0. So, something must have happened to this channel charge, right. So, where do you think, or what do you think happened to this? Do you understand my argument, right? So, the gate was just now connected to VDD, there was a channel charge of mu, I mean Cox times WL times VDD minus Vn minus Vt, and now I have turned the gate off, and we all agree that there is no charge in the channel, the transistor is off. Clearly this charge must have gone somewhere. It has vanished into thin air, right. Where do you think it could have gone? The MOSFET has 4 terminals, it has got the body, it has got the gate, it has got the source, it has got the drain. If there was some charge and then it vanished, it must have gone out through any or all of these 4 terminals. Which do you think it cannot go through? Gate and body it cannot go through, because there is a depletion region on one side and there is an oxide region on the other side. So, this charge must have gotten squeezed out through either the source or the drain or both. Okay. So, without doing any more complicated calculations, it is at this point impossible to figure out how much of the charge went towards the left and how much went towards the right. You understand? Because it must clearly depend on the nature of the impedances on the left side and the right side. You understand? So, there was some nonlinear amount of channel charge when the switch was conducting. When the switch was conducting, of course, just before it was turned off, the voltage across the whole capacitor was Vn. Then we turned the switch off, and some fraction which we as yet do not know of the channel charge has gone and lodged itself on the capacitor, correct. So, if this is C, that amount of channel charge will cause a voltage jump of value. The injected charge, so this is called charge injection. Because the channel charge, when the switch is turned off, at least from the little we know about devices, we are not in a position to predict how much goes back into the source and how much goes into the sampling capacitance. At this point, one thing we can definitely say is that some unknown fraction, which could change depending on the input perhaps, of the channel charge gets on to the hold capacitor. Is this clear? So, if some unknown charge F1, which as we already discussed is a function of the input voltage, gets on to the hold capacitor, that will result in a change in the capacitor voltage by value F1 of Vn divided by C, and this therefore represents an error in the held value. Does this make sense? So, what do you think we can do about this? Any suggestions? We ideally want to make the error as small as possible. See, there are two problems with the error caused by charge injection. One is, of course, it is not the signal that you want to have sampled, right, okay. And two, more importantly perhaps, this error is a nonlinear function of the input that you are trying to sample. Many times in electronics you will find that if something is linear, even though there is a gain error, for example, right, it is usually not problematic in a system because gain errors and offset can be corrected at a system level, alright. So, for example, instead of Vn, if I measured always Vn plus 1 millivolt, this is usually not a problem because I know that that error is constant and does not depend on input. The moment the error starts to depend on Vn in a nonlinear fashion, then it appears as if the input is getting distorted, right, which can be which in fact is a problem in most systems. You understand? So, as far as we are concerned now, we have two problems with the error. One, of course, is that it is causing loss of accuracy, and more importantly, this error is non-linearly dependent on the input voltage. So, the question is, what do you think we can do about this? One tempting thing to say is that I will increase my sampling capacitance. Any comments on that?
If you increase the sampling capacitance at a given speed, you need to decrease the resistance. Thereby, you have to increase the switch size. Again, the channel charge will increase.
Right. So, please note that increasing the sampling capacitance is not, does not solve the problem, because if you increase the sampling capacitance, the RC time constant will now change. The RC time constant will become larger if you keep the same switch. So, in an attempt to bring the RC time constant back to the same value in order to have the same tracking bandwidth as we had earlier, the resistance of the switch has to decrease, which means that the size of the switch has to increase, which means that there is more charge in the channel. I mean, finally, please note that the low resistance of the MOS transistor is fundamentally due to the large amount of channel charge present. You understand? Okay. So, there is no way of reducing resistance while having the same amount of channel charge.
So, while the MOS is turning on, this charge had come in and then it is going out, right? So, it is like cancelling.
No, but what you are looking at is the held value on the capacitor, is not it? So, what you are interested in is the final value which is stored on this capacitor after you open the switch.
But when I close the switch,
when you close the switch, of course, this needs charge and some unknown fraction again of that charge will come from the left and some of it will come from the right. It is likely that it compensates, but that does not really help me because I have already used the information. I mean, all the information is on the held value, correct. The fact that when I turn it on, something comes back does not help me because the input might have changed. You understand? So, the input has changed, right. I need to estimate the input that was there in the previous clock cycle, correct. Now, it is true that when I turn the switch on the next time around, some of this may actually go back, the injected charge, but that does not help because the input is changed.
So, what if the sampling frequency was very high, it is an oversampling, then
okay.
it is going to help because input has not changed much between the.
No, not really, because during the next sampling period, you're still sampling, isn't it? So, all the information is in the hold mode voltage, right. The held voltage is simply the input plus some injected component. Okay. So, one thing that is that is apparent is that increasing the size of the sampling capacitor is not really helping, because in order to maintain the same time constant you want to make sure that this error is, I mean you got to make sure that the resistance of the switch scales in the same manner as the capacitance, which will bring us back to an increased amount of injected charge and increased capacitance, the two cancel out. Okay. All right. So, as I said, in electronic system design often gain or offset errors are benign errors, in the sense that their offset can of course be corrected given its constant from cycle to cycle. Gain error can be is often acceptable because it is a linear phenomenon, right. So, we know that we now cannot use this kind of sampling scheme without incurring significant nonlinearity in the form of charge injection, okay. But we will at a pinch be willing to accept a solution where there is an error, but if that error is either a linear error in the form of a gain error or in the form of offset, then we will not be too worried about it, okay. So, finally, in order to sample or and hold on to this capacitor C, there must be a switch somewhere, correct, okay. So, one way of thinking about this is to say we already have a switch here, earlier the bottom plate of the capacitor was being connected to ground, correct. I mean in principle there is nothing wrong if I use another switch in the bottom plate, correct. I mean you might wonder why use two switches when one is good enough, is not it, right. So, this is exactly identical to having, in principle there is no difference between this and the earlier circuit where he had only one switch, both of them accomplish the job. But there is, and finally if you want to implement this with switches, with transistors, this is probably what we would do. Okay. Can you comment on the charge in this transistor and the charge in this transistor?
Output depends on this input signal.
This charge is WL times Cox times VDD minus Vin minus Vt blah blah blah, right. So, this is basically some function of Vin, whereas what is the charge in this channel? It is some constant Q naught which is independent of the input, correct. So, even though in principle these two switches seem to be doing the same thing, and we do not seem to be gaining anything from these having two switches rather than one, we see that there is a crucial difference. A crucial difference is that the charge in this switch is input dependent, whereas the charge in the bottom switch or the switch in the bottom plate is independent of the input, alright. So, we have turned both these switches on in order to sample the input voltage on the capacitor C. Then we need to, in order for the input to be held, we need to open the switch. So, what do you think we should do? We would turn both these switches off. So, is there do you think, I mean obviously you can either turn the top switch off first and the bottom switch later, or vice versa, or both at the same instant of time. Okay. So, what do you think is a reasonable thing to do?
Bottom should be turned off first.
Okay. So, and why would that help?
That while turning off the top switch, that charge will not.
Very good. So, it makes sense to turn off the bottom plate first, right. So, you turn this off first. So, what happens when you turn the lower plate off? Again some part of this channel charge will go to the left and some of it will go to the right. We do not know what fraction goes where. So, however, the charge in this channel is constant and independent of the input, okay, which means that this injected charge will cause an error on the capacitor voltage, and that error will be Q injected divided by C, with the difference from the earlier case being that Q injected is independent of the input. Does it make sense? All right. So, now if this transistor is turned off, this is the situation we have here. The top switch is still on, right, and we are getting ready to turn it off, and there is a charge in the channel which is non-linearly dependent on the input. Now, when you turn this off, what do you think will happen to this charge? Whatever we know or we do not know about the dynamics of charge injection, one thing is for sure: if on one side there is an open circuit, charge cannot flow in that direction. So, now when you turn it off, all this charge which is signal dependent goes into the source. Okay. So, the voltage on the capacitor is basically the input voltage minus Q inject by C. So, there is an error on the sample voltage, however, this error is independent of the input. Okay. So, this is another very crucial circuit technique that is used routinely in switch capacitor circuits, and this is called bottom plate sampling, often drawn in this way. So, this is phi 1 and this is often called phi 1a, where phi 1a so this is phi 1, phi 1a is something which needs to fall to 0 before phi 1 falls to 0. Right, and the reason for calling this phi 1a is this is an advanced version of phi 1. So, phi 1a is an advanced yes.
Ground the bottom plate of the capacitor once you open that phi 1.
Once you open phi 1, pardon?
Other.
So once you open phi 1, the capacitor is floating. Both ends are floating, which is a perfectly legal thing to do, right?
How is it going to be used by
that we can figure out later, right, because you have these two ends. I mean, you now can think of this as you have a capacitor with some voltage across it, right. Now this voltage is a good reproduction of the voltage you wanted to sample. Now what you do with this floating capacitor is up to you. You understand? In fact, this is exactly what you want. You want a capacitor with both terminals accessible with the voltage you want on the capacitor. If you had if you had a grounded capacitor, that is constraining you in some respect, right, because you are now constrained to work with a capacitor where one terminal is at ground. Okay, you understand? I mean, it's as if somebody took the input voltage, converted it into charge, put the charge on these two plates and then gave that capacitor to you, right. Now how you use it is up to you. Yes.
So like in the bottom transistor, charge is fixed. I mean, it's independent of Vn.
Yes.
But the fraction of charge that is going into the C.
Correct.
Why should it be constant? Because
the fraction of charge that goes into C will, I mean, it turns out that it depends only on the ratio of the impedance it sees here on the left to the impedance it sees on the right. For one, the impedance it sees on the left is very, very low because it's ground, right. So most of it will go to the left, right, a small amount will go to the right, and that impedance remains largely fixed, okay, regardless of the input.
because impedance seen on the other side is not only C, but also the further the resistance of the transistor.
It is the resistance.
That
So
itself is varying with
that is varying mildly with this thing, and more importantly, the impedance of the source
source itself.
is also there. That you assume to be constant and does not change with input, right. So this fraction, of charge, is a very, very, I mean, you are worried now about the change in the fraction of the small injected charge which is independent of the input, right, and that turns out to be extremely small. Okay. I mean, charge injection in MOS switches is a problem that has been addressed, in many ways. So you can actually write the complicated differential equations that govern the MOSFET, and depending on the gate waveform and all this, you can actually go and calculate how much charge goes which side. Okay. But unfortunately, that analysis is not really useful. It of course gives you insight into MOSFET operation, all this stuff, but there is no point in analyzing a complicated problem when a simple solution exists, correct. Okay. You understand? I mean, there is no point in trying to figure out, in how many ways you can fall, right. Okay. The solution is to walk carefully. You understand? That's a lot easier thing to do than write computer code to figure out what will happen when you make put a wrong step. Okay. So this is one of those things. You can write a lot of interesting stuff about how much a charge goes where, but that charge injection is not desired, correct, and there is an easy way of fixing it, and it turns out that this simple thing is what is called bottom plate sampling. And is a very, very common, in fact it is universally used in all switch capacitor circuits. When you want to sample a voltage on a capacitor, you always turn off the bottom plate first. Now one question that you might ask is, how much time do I need between turning off the bottom plate and turning off the top plate? I mean, an inverter delay is all that is needed. Okay. So these do not have to be big delays, a small delay is good enough. So often the clock generator, as you can see, now is becoming more and more complicated. This is the core of the non overlapping clock generator. phi 1 and phi 2 are non overlapping clocks. Okay. Now, you want phi 1 bar, these are the complements, okay. And so, if you call this phi 1 and you call this phi 2, both of them are still non overlapping. You understand? Please note that these two are non overlapping. So, these two are non overlapping too. So, obviously, it is impossible to advance a clock in, I mean you can't advance a signal, you can only delay it, right. But since, so if you call this phi 1, you can call this, it is not as if you derive phi 1 a from phi 1, you derive phi 1 from phi 1 a, you understand. So, this is, you can call this phi 1 a and phi 2 a, both are advanced versions of phi 1 and phi 2, okay. And you can generate complements by, I mean by picking off this signal and so on, you understand. And you can also play around with the delays of these inverters, right, to play around with the time you have to advance phi 1 a with respect to phi 1. And then the delays of these NAND gates will tell you how much non overlap time you have between phi 1 and phi 2, okay. And finally, these clocks will be used by several blocks. It is not as if you just generate one phi 1 and phi 2. For example, in the various switches we have seen that some switches need phi 1, some need phi 1 bar, some need phi 2 bar, all sorts of stuff. So, it is not as if these inverters will be driving only one inverter load or something like that. Often these also have to be will be used by other blocks in the A to D converter. So, there will be a significant load on the clock generator. So, you need to put adequately strong digital buffers to make sure that the various blocks which need phi 1 and phi 2 are being supplied with these signals without degradation too much of rise and fall times, okay. And of course, you must also make sure that whatever skews you have in the clock generator are, or non overlap times you have in the clock generator are reasonably accurately reproduced at the site where you want them, you understand, which means that the drivers which sense the signals and drive the logic gates must A be sufficiently strong, and you must make sure that the skews between those drivers is as small as possible, so that you don't mess with the what do you call the timing relationships between the clocks at the clock generator end versus what happens later. Is this clear? All right. So, yes.
How do you size the other MOSFET? I mean that bottom plate, that MOSFET. How do you size that MOSFET?
Well, okay. The question is, how will you size this transistor and this transistor?
I mean the one in this, the phi 1 I know that depends upon the.
Now what do you think is the tracking bandwidth?
That will be determined by phi 1a.
No, it will be determined by both phi 1a and
plus phi 1.
now you think of these as two resistors in series,
Okay.
right. So, you have to make the resistors sufficiently small so that you hit the tracking bandwidth, okay. And this also brings out another minor point, that is, you do not need to make the switches any larger than is necessary, okay. Let us say you have a spec on tracking bandwidth, alright, you have some safety margin, alright, and you decide to choose a certain switch size, okay. Now, there is no point in choosing 5 times the switch size, and why? Because it does not help you improve on your spec in any, when your tracking bandwidth spec is so much and some size plus safety margin allows you to reach that spec. Choosing a switch size which is much larger than what is necessary is often counterproductive for a couple of reasons. One is that charge injection will unnecessarily increase. You understand, we all understand that there is charge injection because of the bottom plate switch. If you make the switch much too large compared to what is actually required, all that it means is that the amount of charge injected will be more. It is still independent of the input signal and all that, but it is unnecessary. A further problem is that somebody has to drive these control signals, you understand. So, if you go on blindly thinking bigger is better and make switches which are much larger than are really required, then you will end up with a situation where the clock generator, right, will now have to drive huge capacitive loads, and those drivers will start to guzzle a lot of power, completely unnecessary, because you did not need such big switches in the first place. So, the strategy to make these circuits work is A, choose switches which are large enough, but do not overdo it. Okay, if your switch size is too small, things will not track properly. If the switch size is too big, you will unnecessarily end up with charge injection problems as well as unnecessarily driving a lot of parasitic capacitance, which will lead to a lot of unnecessary power dissipation. You understand? So, going forward in the next class, what we will do is see the following. I mean, we have learnt now to design a very crude sample and hold. In other words, we have learnt how to take a continuous time input signal, right, and sample it on a capacitor without too much either distortion or charge injection. Okay. So, when we design a circuit like this, the first thing we would be interested in is figuring out how good is it, I mean how good is good, right. We must have some metric, or we must have a way of figuring out how good a sample and hold or how linear a sample and hold we have made, you understand. So, if you are given an amplifier which operates completely in continuous time and told go and measure how linear this amplifier is, what do you think you will do? Here is an amplifier, I am claiming it is very linear, I am selling it to you. How will you make sure that I am not lying to you? What will you do? Or what test will you subject the amplifier to make sure that the linearity I promise is indeed there? So, a common thing to do is to apply a sinusoid, which itself must be very clean, right, and then look at the output. If I am indeed giving you a linear system as I had claimed, the output should also be sinusoidal, it must be free of harmonics, because a linear system by definition cannot produce harmonics. So, the level, I mean no real system will be perfectly linear. So, it is only a matter of how small the harmonics are. So, if I have within quotes a very linear system, I can expect that for a given agreed upon input amplitude, the level of the or the amplitude of the harmonics is very small, right. So, in other words, putting a harmonic sinusoidal input and measuring the harmonic strengths is a standard, well known, well accepted way of measuring the linearity of a system which operates in continuous time. Now, we have got a slightly different problem, we need to find the linearity, right. However, the input is continuous time, whereas the sampled output is naturally discrete time, okay, and we would like to, since we have been comfortable with using sinusoidal test signals to measure linearity, we would like to be able to do the same thing even for this particular system. We would like to put in a clean pure sinusoid and measure within quotes if possible the harmonic distortion that occurs at in the samples of the sample and hold. You understand? But there is something that we need to be aware of. One thing is that if you take a sinusoid in continuous time, which is naturally periodic, and you sample it, the discrete time sequence, as we have seen, need not be, even though the input continuous time signal is periodic, once you sample it at some rate fs, the resulting discrete time sequence need not be periodic. Okay? So, I mean if this discrete time sequence is not periodic, then it hardly makes sense to talk about harmonics, because a non-periodic signal, I mean what is the meaning of harmonics and all this? It means, I mean harmonics or distortion is a simple way of saying this following complicated thing. I take the output of a continuous time system, decompose this into a Fourier series, right, and give you the Fourier coefficients. That is what a harmonic distortion test is, right. If the discrete time sequence is not periodic, then it does not make any sense at all. So, there must be some way of choosing, because not all input sinusoids after sampling will result in a periodic sequence. We must find, or we must be able to excite the sample and hold with only those sinusoids which after sampling will give us a periodic sequence. Okay.